Hello PCH, and here is a short video for our last section. So this is going to be just about solving for f of x when f of x is a rational algebraic equation, and also looking at any potential domain restrictions. So the first thing we noticed in this first example is you have a quadratic divided by x minus 3. So right off the bat, we know that we have a restriction that x cannot equal 3, and we want to keep that in mind when we go through to solve the equation. So they want us to solve this when f of x equals 4. So I'm going to take my x squared minus 5x plus 10 divided by x minus 3 and set it equal to 4. Then the first thing we're going to do is cross multiply. So that gives me x squared minus 5x plus 10 is going to equal 4 times x minus 4 times a negative 3. And so we have this equation, and we want to combine all our like terms and set it equal to 0 since it's a quadratic. So I'm going to have x squared minus 9x, add 12 gives me plus 22 equals 0. Now I don't think I can factor that, and I don't want to do completing the square because 9 is an odd number, so it looks like quadratic formula would be my first go-to, and I always like to do my discriminant first, and the reason for that is twofold. One, it's the hardest part of your quadratic, so if you do that first, you're just plugging it in underneath the radical. But if you get lucky and you get a negative number, and we're not going to be dealing with complex solutions, we would be done. So your discriminant is just the b squared minus 4ac part. It's the part that's underneath the radical, without the radical. So b squared is going to give me 81. Minus 4 times 1 times a positive 22. So 81 minus 88, I don't even really care what that is. All I care about is that is a negative number, which means I'm done. I have no solutions because they would be complex. Ah, that was friendly. Okay, let's go on to a little more difficult one, and mainly we did that example because I wanted you to see what happens if you have to factor or do a quadratic, and notice that by doing the discriminant it saves you a lot of work than doing the whole quadratic formula. Alright, so in this next example we can see from the first fraction that we're going to have the restrictions x cannot equal a negative 2 or a positive 5, and it actually turns out, let's see, we have this equals that. Let me see, I can factor this one exactly the same. Ooh, that was good. All right, so we have the same restriction. Now notice, this is kind of like your partial fractions. So what we're really doing is trying to solve for that x in the numerator, but let's go ahead and see how we would do this. So I'm going to make a common denominator on both sides. I'm going to circle our restrictions here. So that means this first fraction is going to need x minus 5, and this one is going to need x plus 2. And we will continue down here. So I'm going to have on top x squared minus 5x plus 7x plus 14. There was a plus there, so everything's kept their same sign. That was just distributing, so now this is over the common denominator, x plus 2, x minus 5, and that is set equal to what they gave us, 14 over x minus 5, x plus 2, same denominator. Since the denominators are the same, I can ignore them. Those part are already set equal. What I'm working on is the numerator. So I want to set this equal to 0. So notice, this one's going to be kind of friendly, because if I subtract 14 from both sides, I'm going to get x squared minus 5x plus 7x equals 0, because the 14s will cancel each other out. So I have x squared plus 2x. So this is a good example of just pulling out your GCF. And we notice then when I set this equal to 0, I'm going to get either x equals 0 or x equals -2. But now we go and look at those initial restrictions and we see that x equals -2 is extraneous. It's not allowed. So my only solution is x equals 0. And we're done. All right? Awesome.